Popcorn tin. Get the grass block. Grass block. Wait, are you gonna go AMC? No, I'm gonna see the police. Can you get chicken chocolate? Minecraft? Did you? Oh yeah, you did. No, I watched it and it's the Star Wars. Yeah. Now I did get my phone Minecraft block, but I was watching it on two computers. Oh, man. Here's me complaining about it and I'm the iPad. I agree. I'm seeing you guys 65. Yeah, I know it wasn't. Professor,
What's up?
for mechanical, do we need a C to pass?
No, D minus above. Pass.
But isn't this class like a prerequisite for like?
It is, but it doesn't count as so for your math and physics and chem courses, those you need a C or better.
Yeah.
All the engineering courses, well, the labs are different. The labs you need a C or better, but for all the other engineering courses, it's D minus and above.
Oh.
Yeah. Even the prerequisites.
Yeah. So we have this class. We transfer P transfer. What is the last class? I'm not really worried. Yeah, I think I'm doing, I cleaned it up for it. No, I mean, I think I repeated it. I don't know what I have. If you want to know what I have. I don't. I know only lots of I lost full credit for one of the problems. And then passed over, and I only got one, yeah. Or. You think I want. I'm glad because I would be mostly about the columns and I knew it was like either case or one case. And I picked up the case, I got it fully wrong. I should have written out the case.
Yeah.
Thank you. I get over it. For me,
All my ones.
oh,
All
yeah.
four.
You can be, oh, I don't know if you've done it, 'cause I don't know when it,
Yeah.
when it's rescheduled, right?
And I was like,
Like,
oh,
I don't.
well, but it's like, no, like, they're gonna look at you and you're just, I'm not even take, put in the ticket for it. Cause then,
Yeah.
like, I can do the final, and then like, the ticket on Monday.
Yeah, I don't know.
I'm doing this, and like, to the next
Well,
one.
yeah, are you taking it in the? Yeah. I don't know, I think we can. Because that's what I think we're going to, for the term for Cal 4.
But they only take it.
No, they didn't take it out there. Yeah, I was like, okay, it's because I have class right after. You can cover that. At least you're everything
Like,
like,
should I do that?
I mean, if you really need the time and you need to spread it out.
Oh,
I'm pretty sure they
well,
can
look
let
at
you.
these socks. So, like,
Yeah, that's what I'm saying, right? That's what I'm saying. Because I have asked for that too, to have it at a different time. Because it's like, dude, I'm just saying four finals in 1 day. Yeah. Yeah. So you can ask, I don't know, I'm pretty sure somebody was like, we need to, you put it into the office.
I'm
space,
probably
And I don't know,
I'm gonna have to contact all of them.
I mean, I just have it, they're like, oh.
I'll be honest. I don't know if they're aggressive.
I'm sorry.
Oh,
I
sure.
think you're okay.
Have you started?
Extra minute, 2 8, and then whenever we go. Well,
It's like a great month. I was like, I don't know if I want it. Like, look into that, I went to the station.
So whenever you said like this, I just make.
I don't know when it's due. I think by end of this week.
So like that
too.
takes like.
You schedule it like, oh, yeah.
Tomorrow, you change. Oh no.
That's good, yeah.
I already saw this.
So you can like I said, email your professors.
And then the
I'm just saying, you know,
Yeah.
for you to have one, 'cause, dude, I'm open. 'Cause I had that shit too. I think even two on the same day was like, okay, I mean, it's.
Oh, and they usually have a section where they're. Yes, well, that's when it's changed.
Like, you can also ask if there are questions about their classes. You can also, can I make it? No,
And that way it's not that many devices, set up to take like, so.
that's what I'm saying.
Yeah.
Worst case, you're like at 10, because I had a schedule my. Yeah.
I don't think you did, but I didn't change.
I'm thinking, a lot of the stuff I don't, the only time is. But I'm stressed, my eye flutters, so that's why sometimes I don't think out there, because I'm just staring at this, and it looks like I'm looking at something. And I was like, oh. Yeah, I'm always staring at something, one time.
All right, it's 4 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Good to hear. We are very quickly winding down the semester. So we have 4 more lectures. So we have today, Thursday, and then Tuesday, Thursday next week as well. So I'm targeting, I'm hoping to finish up everything by next Tuesday. So that next Thursday we can kind of devote the whole class session to just review for the final. So at the very least, next Thursday is going to be all review. We may finish before that too. So I think I'm going to need everything this week to finish up. And maybe, maybe half of the lecture or 2/3 of the lecture on Tuesday to finish up everything as well. Okay. But that's my plan. So my plan is finish up all new content by next Tuesday. Next Thursday, we'll review for the final. Okay. Speaking of the final, hopefully everyone got my email yesterday about the final exam. So I sent out that email and I realized I forgot to mention when the final exam is going to take place. So final exam is going to be on Tuesday of finals week. So that's Tuesday, May 13th. It's going to be in the 5 p.m. to 6:50 p.m. slot. So we'll be here pretty late. So, probably it's going to be your last final of the day that day, maybe. But that's when this final is going to be. Okay. All right. So format for the exam, it is a longer time slot than what we have for the midterm. So the exam is going to be a bit longer. So what I'm thinking right now is to have 8 short answer questions and 3 problems. It's a little bit of a different format from the practice exam that I posted. So if you've had a chance to take a look at the practice exam, the practice exam was 6 short answer and 4 problems. But that one's a little bit long. And so for this one, I'm trying out to see if maybe 8 short answer, 3 problems might be a little bit more palatable, I guess, to say. Okay. And if you kind of do the math a little bit, we basically have done 3 big units in this class. So we have everything from midterm 1, everything for midterm 2, and then everything after the second midterm. So all this probability and stat stuff. So you can probably expect, 1 question from the first midterm, 1 problem from the second midterm, and 1 problem from probability statistics. I feel comfortable saying that you can expect that. Now the short answer questions probably will be, a 1/3 split for each one as well. Maybe with a bit more emphasis on the new stuff that we cover. Okay. Okay, so with that said, because the exam is longer and covering more content, you are allowed to bring 2 cheat sheets. And so 2 8.5 by 11 cheat sheets for both you can use both sides. Forgot to mention that. Okay. I know what some people have been doing is that you can you're just bringing several cheat sheets but just having them single sided. So 4 sheets single sided is okay, or 2 sheets both sided is either one is fine. Okay. Now the main thing that you should be looking at, or I would say the first thing that you should look at when you're studying, is the study guide. So definitely take a look at that, because even though the final exam is cumulative, I did cut out, maybe about 1/3 of the class, because it's going to be impossible for me to tell everyone everything in just a single 2-hour exam. So definitely look at the study guide to help you prepare, and definitely make note of which topics are not there, so that you can avoid studying for them. Just because I know you guys have probably 3 or 4 other exams, and so you want to be efficient with your time when you're preparing for these exams. So definitely only study what's on the study guide. I'm not going to ask you anything outside of what's on that study guide. Okay. Okay. So the other announcement that I made yesterday is that homework 7 is posted. So homework 7 gives you practice with the probability and statistics stuff that we've been covering. So you should be able to do maybe about 1/3 of it at this point. So today we're going to go over hypothesis testing, which is problem 3 on the homework. And then I'm hoping that by next Tuesday, we'll finish up linear regression, which is what you're going to need for the last problem on homework assignment. Okay. It's a bit of a more fun homework assignment. It's a little bit untraditional. So what you'll notice for these probability and statistics stuff is that the number of calculations that you're doing is a lot less than what we've been doing in terms of, when you compare it to like Laplace transforms or Fourier transforms or differential equations. So, the homework 7 was meant to be a little bit more fun than the other homework assignments. So, yeah, definitely have a bit more fun with them. Okay. All right. And so plan for today is I have one more example to do with confidence intervals. And so we're going to do that today. And then we'll move on to hypothesis testing and quality control. Okay. All right. Any questions I can answer before we get started for today? Okay. Other thing. So I posted your grades for the second midterm this morning as well. So just like I mentioned last week, there's two grades for your midterms online. But remember, for this class, whichever midterm you score higher in, I weight that one as a higher percentage of your score. So, if you did better on homework 2, if you did better on midterm 2, what you're going to see is that I swapped that score into your midterm 1 spot. So, it's not that you scored, well, some of you actually scored exactly the same on midterm 1, midterm 2. But then for others, you didn't get the same score in midterm 2. It's just, you scored better in midterm 2. I just swapped into the midterm 1 spot, just to help your grade. Okay. So I have them ready for you guys today. I actually forgot to compute the average just because with the swapping, I don't get an accurate, number for the average, but you guys did score better on midterm 2 than midterm 1. So I would say the average is probably in the ballpark of like 38, 39 out of 50. But I didn't formally compute it. That's just my opinion. Okay. Okay. All right. So let's go ahead and pick up where we left off last time. And so what we were discussing last Thursday was confidence intervals. Okay. Okay. So the whole idea with confidence intervals is that, when we're talking in the world of, probability and statistics, almost everything that we observe out in the real world has some kind of random variance to it. Okay. Okay. So even if you observe the same phenomenon twice, there's always going to be some uncertainty in terms of, how that event was going to unfold, or even just how you observed it, how you measured it to begin with. Okay. And so instead of stating some things as fact, where we say, we have our variable x is equal to 5, right? What we can say instead is that x is in a range, right? So we'll say x is between, 4.7 to 5.3. Okay. Right. Where this range here on the right, shows that there is some uncertainty, there is some variance in the measurement or the observation or the calculation of our variable x. Okay. So right now we're kind of in the process of, how do we take a random observation or how do we take some kind of random event and really quantify the amount of uncertainty that there is in the observation of that event. Okay. Okay. And so the way that we do that, the way that we quantify this this uncertainty is through a technique known as confidence intervals. So basically, reporting our, our quantity as if, as if there's a range, okay? Okay, but the thing with confidence intervals is that, there's actually kind of two parts to it. And so on the one hand, we have our range. And so we have a range of values at which our variable can take, right? Right? So that part's fairly straightforward, right? So anytime you have a random variable or a random quantity, right? We know there's going to be some variance in the value. So we express that as a range of possible values, right? But the other part of confidence intervals is that we have to have some level of confidence in our range, usually expressed as a percentage. Okay. Okay. And so, for example, right? I keep coming back to this example just because it's, it's part of my everyday life. I experience this every time I come to work, but it's my commute time, right? Should probably use a different example. Maybe on Thursday I'll come up with something different. But my commute time, this always varies, right? It's never a consistent value. Every time I observe this or every time I experience this, it's always going to be something a little bit different, right? And so what I can say is T here is going to be equal to, anywhere between, 35 and 45 minutes. Okay. So that's the first part, right? And so the other part of this is that, I have to give a level of confidence in this. And so, I give this range here. So I say that, my commute time is between 35 and 45 minutes. And my confidence in that prediction is, say, 90%. All right. So whenever you have a confidence interval, you need to have both things. So you need to have both your interval and you need to have the level of confidence that you have in that interval. Because what you're saying is that the next time that you observe your commute time or the next time that you observe this variable, there is a 90% chance it's going to fall or the value is going to fall within that interval itself. Okay, so that's the concept of a confidence interval, right? And so what we did last Thursday was we did an example of how to compute this. But we did it for an example where we knew the precision or we knew the uncertainty in the measurements before. Okay. And so if you recall, the specific example we did was that, we were measuring or we had a group of people measure the length of a smartphone using a ruler. but everyone was using the same ruler. And so, so we knew what the precision of that ruler was ahead of time. So, we can use that precision to help predict our confidence interval. Okay. And so that's usually the case when you're finding the confidence interval on something that you can directly measure. Okay. And so it's usually the case when you can directly measure the random event, and there's very limited amount of outside uncertainty that comes with the measurement. Okay. So, for the example we did where, we're just taking a simple measurement of a smartphone, there's really not a lot of random events that can occur, right? There is, the random possibility that, we get someone that, maybe forgot their glasses for the day, or maybe forgot their contacts, so they're not able to see the markings clearly. But, that's probably a fairly low chance. So for such a simple event, for such a simple case with, where we can directly measure the event, and there's very limited amount of uncertainty, it's usually pretty safe to assume the precision or the uncertainty before. Okay. And if you recall from last Thursday, what that precision was the precision on the measurement device. And so in order the precision on the ruler that we're using. Okay. But in most situations, where there is a lot of outside uncertainty, or maybe you're computing the uncertainty or the confidence interval on something that you cannot directly measure, something that you're computing, you can't assume the precision ahead of time. Okay. In other words, another way for us to say this is that our variance, the variance in our unknown event is unknown at the beginning. Okay. And so for cases when our variance is unknown, that does change our procedure a little bit. It's the same basic idea. So, the same kind of process that we're going to go through is very similar to what we did in the example last time. It's just that we have to shift what we do just slightly and look up in a different data table when our variance is unknown. Okay. So I'm going to review what that process was today, and then we're going to do an example. That should take up maybe about half of our time here. And then we'll move on to hypothesis testing from there. Okay. All right. But that was just mostly a review from last time. So a little bit of a lengthy review, but it is kind of a new concept. So I wanted to make sure I reviewed that. Any questions on this so far? Okay. All right. So let's review the steps to computing the confidence interval when our variance is unknown. Okay. Okay. Step one. All right, so just like we did in the previous case when we knew our precision ahead of time, the first step to computing confidence interval is to first of all, set the level of confidence. Okay. So you're going to set a confidence level gamma. Okay. And remember, that's going to be a decimal between 0 and 1, probably something closer to 1, because you want to be fairly confident in your interval. Okay, step 2. After you've set your confidence level, you're going to compute the following quantity. You're going to compute, you're going to take 1/2 multiplied by 1 plus gamma, okay? And that's going to equal f of c. So that f of c is something that we're going to use together with something known as the t distribution, which is that data table that we went over at the end of class last time. Okay. Oh, actually, this would be a good time at this point too. So the other thing you're going to compute here is what's known as your degrees of freedom. Okay, because you're going to need that to look up things in the table as well. Okay, so your degrees of freedom is just simply n minus 1. But remember, n here is the number of measurements or the number of samples that you took of your random variable. Okay. So then once you have these two pieces of information, so you have your f of c value and you have your degrees of freedom, you can then look up a basically a k value, or excuse me, you can look up a c value in a data table. Okay. And just like we mentioned last week, this data table is computed through something called a t distribution, which is a special kind of random variable distribution that's specialized for computing confidence intervals. Okay. All right, so I'm not going to write the whole table again. I think I mostly did that last time, but I'm just going to summarize it here. Okay. All right. So first thing you need to look at is you need to look at the column for f of c. Okay. Okay. So the f of c column here, this is going to have several values. Okay. And so based on what you compute from f of c from before, right? So based on what you computed from this step right here, right? That's going to tell you which row in the table that you're going to look up. Right? So for instance, let's say that you set a confidence interval of 0.8, right? Right? So you plug 0.8 into this formula here. So you get 0.8 plus 1 divided by 2. That's going to give us 0.9. So that means our f of c is going to be equal to 0.9 based on that formula that we have above. Okay. And so that tells us you're going to look at the row for f of c is equal to 0.9 in the table. Okay. So that's the first thing you should do. So you should look at your table and find out which row that you're going to be looking at based on your value for f of c that you computed in this step. Okay. Okay. And by the way, this table goes beyond this. And so, of course, a confidence value of 0.8 is fairly low. But there's a lot more values in the real table for like 0.925, 0.95, 0.975, so on and so forth. Okay. Okay. The other thing you should do is the rest of the entries in the tables here are sorted by the degrees of freedom. Okay. Right, so each column here corresponds to a different number of degrees of freedom, right? So we have 1, 2, 3, 4, and of course it goes beyond. And so if you have a lot of measurements, and so it's captured in this table as well. So it goes up to 10, 11, 12, so on and so forth. Okay. Okay. All right, and so based on the number of measurements or based on the number of experiments that you did, you can look up on this table and find the column that corresponds to the number of degrees of freedom that you have. Okay, so let's say for this experiment here, we conducted 11 measurements. Okay, and so that tells us our degrees of freedom is going to be 10. Okay, so the column that you compute or the column that you look at is going to depend on how many experiments or how many measurements that you did. Okay. All right, and so wherever these two circles intersect, okay, there's going to be a number here. And so there might be a number, let's say it's like, 1.48. This right here is going to give you your value of C. Okay, and then we're going to save that for the next step. But the most important thing for step 2 here is to find the value of C for your measurement based on the level of confidence that you want and based on the degrees of freedom that you have from your measurements. Okay. Okay, so that's what step 2 is all about. So step 2 is all about computing the right value of C for this confidence interval. All right, any questions on this so far? Okay, good. All right, next thing we're going to do, step 3. Okay. So step 3, you're going to compute the sample mean as well as the sample variance from the measurements that you did. Okay. So, I've written the formulas for those probably 2 or 3 times already. So, you guys know how to compute mean and variance from the data set. Okay. All right. And then finally, the last step is once we computed, the value for C, we've computed the sample mean, sample variance. We are now ready to compute our confidence interval. All right, so step 4 is to compute K, where K here is C that we got from step 2. S, which is the standard deviation of the measurement. So you take your sample variance and you just take the square root. Okay. And then you divide by the square root of n. Okay. All right, and then once you have your value for K, then you can define your confidence interval as the following. So your confidence interval is x bar minus K, okay, which is less than or equal to x, which is less than or equal to x bar plus K. And so this right here defines your confidence interval. Okay, so it's a little bit more of an involved process. There's, probably 2 more calculations than you have to do when you compare to the previous example. But, it's fairly straightforward process to do this, okay? It sounds like there's a lot of steps, but then once you actually see it in practice, you'll see that it's not that bad. The worst part is just looking up the entries in the T distribution table. All right, any questions on this before we jump into an example? Okay, all right, so let's look at an example. All right, so this one has a little bit more of an engineering flavor compared to our previous examples. But let's say that we want to, we're interested in computing the flash point of diesel oil. Okay. So the flash point essentially is the temperature at which, when you heat up oil to a certain point, that's when it starts to kind of flash and splash and kind of start to, that bad stuff usually happens when you reach the flash point of an oil. That's when usually things, bubbles form and they kind of pop and things kind of flash and things light on fire. So, usually, if you're dealing with oil in any kind of capacity, this is something that you want to know. Just to kind of keep yourself safe. Okay. All right. So let's say that we perform experiments and we have the following 5 measurements. Okay. So first experiment, let's say that we got a flash point of 144 degrees Fahrenheit. Second experiment, we got 147 degrees Fahrenheit. Third experiment, we got 146 degrees Fahrenheit. Third one, we got 142 degrees Fahrenheit. And the last one, we got 144 degrees Fahrenheit. Okay. Okay, so you can see there's quite a bit of variance here. So, we didn't get the same thing. So basically what we did with this experiment is that we heated the oil and we measured the temperature throughout. And then as soon as the oil started to flash, then we stopped the experiment and we observed what the temperature of the oil was. Okay. Okay. Now, what's interesting about this is that, because flashing is, quite a, there's a lot of uncertainty with the process because it depends on how the heat propagates through the oil. It depends on convection of the heat within the oil itself. This is not a situation where we know the variance ahead of time. And so with that in mind, and with these measurements, what we want to do is we want to determine the 99% confidence interval for the flash point of diesel oil. Okay. All right, so that's the setup for the problem. Any questions on just the setup for the problem? Okay. All right, so let's go ahead and run through our 4-step process here. Okay. Okay, so step 1. So step 1 in determining the confidence interval is that we have to set our confidence level. So luckily for us in this problem, this was given to us. And so we know that we want to find the 99% confidence interval. So that means our value for gamma here is going to be the decimal form of that percentage. And so it's going to be 0.9. Okay. Number 2. So step 2, this is where you're going to do most of your work here, because you need to do a couple calculations, and then most importantly, you need to look up the value for C in the table. Okay, so first thing we're going to do is we're going to compute f of C. Okay. So f of C, remember, is 1/2 times 1 plus gamma. Okay. So we just do some very quick math. We see that our f of C here is going to be 0.995. All right, so next thing we're going to compute is our degrees of freedom. So the degrees of freedom is just the number of measurements that we had minus 1. So since we had 5 measurements here, right? So we have 1, 2, 3, 4, 5 measurements. Okay. That means our degrees of freedom here is going to be n minus 1, which is going to be 4. All right. And so with both of these pieces of information, let's look up the table for the t distribution. Okay. By the way, for the exam, this table for the t distribution, this would be something I'm going to provide to you. I'm going to make it part of the exam and print it out with everyone's exam. And so, this is not something you have to put on your cheat sheet. So, I'll provide this. Okay. And so if we look up table. So if you're following in the textbook, this is actually table A9 for the t distribution. Okay. So that table is going to look something like this. Remember, one column, the leftmost column is going to be f of C. Okay. And so eventually you're going to find a row where the f of C is 0.995. Okay. And then for the other columns, you're going to look up the one that corresponds to our degrees of freedom. So we have 1, 2, 3, 4. Okay. Right. And so you look at the intersection between this row for f of C of 0.995 and the column for degrees of freedom equal to 4. Okay. Okay, so you look up both of those things and you find in the table that the intersection is 4.60. And so based on this, we can say that C is equal to 4.60. Okay. Okay, so now that we know our value for C, we can move on from this step. So of course I did this fairly quickly, but but it's hard to kind of simulate the table here when I'm writing. Okay, next we have step 3. So once we have our value for C, we can go ahead and compute our sample mean. Okay. And so our sample mean is simply just the average of all of the measurements that we did. So this is 1/5 multiplied by all of our measurements here. So we have 144 plus 147 plus 146 plus 142 plus 144. Okay. We're simply just taking the average of all of these measurements here. Right. And so what we get from that average is 144.6 degrees Fahrenheit. Okay. All right, so fairly straightforward. And then the other thing that we need to compute here is the sample variance. Okay, so for the sample variance, it's a little bit more involved. And so remember, the formula for sample variance is 1/n - 1 times summation from I is equal to 1 to n of xi minus x bar quantity squared. Okay. Right, so you're basically taking the difference between that particular measurement and the sample mean, squaring it, and then dividing the entire quantity by 1 over n minus 1. Okay. Okay, so if we plug that in here, that's equal to 1/4 multiplied by first measurement is 144 minus 144.6 quantity squared plus second measurement is 147. We subtract the sample mean 144.6 quantity squared plus 146 minus 144.6 quantity squared plus 142 minus 144.6 quantity squared plus 144 minus 144.6 quantity squared. Okay. Okay. So it's a little bit tedious to compute, but at least the arithmetic is fairly straightforward. Okay. All right. So we put all this together, right? We punch all this into a calculator. We get a sample variance of 3.8. Okay. And that, of course, is equal to S squared. All right. So now that we have our sample variance, we can take the standard deviation of our samples. So standard deviation is just the square root of the variance. Okay, so we're going to take square root of S squared. And so that gives us S is equal to 1.95. Okay. Don't be fooled. So this example is a little bit misleading. So remember, square root is not the same thing as dividing it by 2. It just so happens that our variance here is close to 4. And then square root of 4 is 2. That's why we're close to 2, not quite. Okay, so now that we have our sample mean, we have our sample variance and our standard deviation, we're ready to compute our confidence interval. Okay. Okay, step 4, first thing we're going to do is compute K. So K is equal to S times C divided by square root of N. Okay. And so in this case, that's 4.01. We punch in all the numbers. So we have our variance S, our value for C that we computed in part 2. And we just take the square root of the number of measurements, which is 5 in this case. Okay. And so that tells us our confidence interval . Our confidence interval looks like the following. So remember, our confidence interval is X bar minus K, which is less than X bar plus K. Okay. And so we take our sample mean and we subtract our value for K. And so that's going to be 140.5. Okay. That's going to be less than or equal to X, where X at this point, we're defining that to be the flash point of the oil. Okay. And that's going to be less than or equal to 148.7. And all of these are degrees Fahrenheit. Okay. So for cases where the variance is unknown beforehand, we're still relatively following the same process. It's just that step 2 is a bit more different because we have to utilize that t distribution. Any questions on this example here? Okay, good. Okay, so that's it for confidence intervals. So the next piece of information that we're going to go over is testing hypotheses. So this area is actually quite interesting because it has very direct applications to an important part of engineering, especially if you're going to be getting into manufacturing. Okay. And so when you think about manufacturing, right, a lot of time you're manufacturing a lot of parts, you know, or a lot of copies of parts that you're going to eventually sell commercially. Okay. And so a big part of manufacturing is an area called quality control. Okay. And so this area of, you know, how do we test a hypothesis really kind of leads directly into quality control. Okay. Okay. All right. So first thing we're going to do is let's define what we mean by hypothesis. Because it's going to mean, it means we're going to give it a slightly more specific definition here than kind of what you've probably heard in your previous science classes. Okay. Okay, so in this case, a hypothesis is actually, in our context, a hypothesis is actually going to have a numerical value. So a hypothesis is a theory or a guess. Okay. I can spell guess. So a hypothesis in our context is going to be a theory or guess for the numerical value of a certain quantity that we can test for. Okay. So there's two things here that are really important. First of all, you know, our hypothesis has to be something that we can quantify, right? So if you think of a hypothesis in kind of a more broad context, you can hypothesize about, you know, the working model for, you know, how, I don't know, for how mold grows on the side of a house or something like that, right? But that's not something we can explicitly test for. So, you know, we're working with a little bit of a more narrow definition here, where our hypothesis has to have a numerical value. Okay. The other part here that's important is that, you know, we have to be able to test for it. And so we have to be able to validate or test for the numerical value of our hypothesis. Okay. All right. So I'll give you an example. One that's, you know, very relevant, you know, if you're working in engineering, any kind of, you know, physical testing or kind of manufacturing, right? And so anytime you are, you know, manufacturing something or building something, a lot of times you have to buy large quantities of raw materials. Okay. And anytime that you buy large quantities of raw materials, you know, that material is going to be rated in terms of its structural strength, in terms of its weight and density, right? And so hypothesis in this case is, you know, our guess or our theory of, you know, maybe the weight of a certain object that we're looking at. Okay. And so in that case, you know, the vendor has some kind of quantity or some kind of number that they are using to advertise, you know, the weight of their material or the strength of the material. Okay. A lot of times when you're producing something in bulk, right, certain samples of that material may have that weight, some may be overweight, some may be underweight, right? All that kind of comes down to quality control, right? And so in this situation, you know, let's say that we're that vendor, or even let's say that we're the people receiving it, right? We want to test ourselves, right? We want to test ourselves if if the weight of these raw materials actually are what they advertise themselves to be. Okay. Okay. And this is important because, a lot of times, when you're doing engineering work, a lot of your work really depends on, whether these values can be, trusted, whether these values can be, relied upon. And so a lot of times when you make hypotheses about certain quantities, eventually you're going to make some kind of engineering decision based on it. Okay. So what we're going to do, and kind of the process that we're going to go through this week, is, what is the process of taking a hypothesis and testing if it's true based on the evidence that we have or the measurements that we have, available to validate. Okay. Because oftentimes, just like we've been doing with confidence intervals and everything else, right? Oftentimes we're going to have multiple measurements and multiple experiments that we're going to do to test if something's true or not, right? That's just the basis of experimentation and kind of averaging out the uncertainty. Okay. So it turns out, when you do have a collection of tests or collection of measurements, there is kind of a systematic process that which you can follow to tell whether, a hypothesis is true or not. Okay. Because sometimes it can be a little bit uncertain, because sometimes you get some measurements that are in support of your hypothesis, some measurements that are, that invalidate your hypothesis. And so it can be kind of unclear, which ones or whether you can say whether this hypothesis is true or not, when you have, some evidence for it, some evidence against it, right? And so there is kind of a formal process that which we can use to validate this. And that's what we're going to do. Right? Okay. All right. So that's kind of the idea. And so, the unfortunate thing with this chapter here is that the process in which we're going to use to test hypotheses is a little bit I would say, there's not that many steps. It's just, sometimes it kind of feels like you're just doing things just because that's what the method told you. So what I'm going to do kind of instead of kind of telling you the process and then doing an example, we're going to do an example live and then kind of, test the hypothesis within that example. And I'm going to use that to kind of explain the process. Okay. But before I get into that, are there any questions on any of this? Okay. All right. So let's go ahead and jump into the example. Okay. So we're going to take kind of a very similar perspective, right? And so let's say that we are, we are a manufacturer, and part of our work, or part of the, part that we manufacture and sell, there is a structural wire component that we need to, rely on. Okay. So the wire just makes up one component of the of the product that we're manufacturing. Okay. So, we don't make this wire in-house. And so this is something that we purchase from a vendor. Okay. And the vendor claims that this wire can sustain 200 pounds of force before it can break. So that's the claim. So the claim is that, this wire, which, we get in basically very large spools. So if you take any segment of the wire, it can take 200 pounds of force before it basically kind of rips apart. Okay. Now let's say that the product that we're manufacturing depends on this load limit, right? And so if the wire cannot sustain 200 pounds of force, if it sustains, something less than that, then our product is going to fail. Okay. Which, by the way, this is just an example we're doing in this class, but this is usually not how you want to design things in practice. You don't want to design things where you take a component all the way up to its limit. Usually you're going to have some kind of factor of safety, but we're just doing it this way just for this example. Okay. So let's say that there's a certain component in our product, where we need this wire to actually sustain 200 pounds of force. Anything less than that, then our product is going to fail. Okay. So what we want to do is that we want to test our vendor's claim before we actually put this product into production. Okay. All right, so that's the situation. So we have our physical engineering problem, and from that we distill the hypothesis. And so our hypothesis is that this wire can in fact sustain 200 pounds of force before failing. Okay. All right. Any questions on just the just kind of the setting or the the example here? Okay. All right. So let's walk through the process of how do we actually test this hypothesis? Okay. Okay. So first thing we need to do, step one, right? Step one is we need to write out our hypothesis. Now, in this case, it's already kind of written out there for us. But for some problems, you actually need to explicitly write it down because it's a bit more hidden in the problem itself. Okay. So step one, form hypothesis. Okay. We're going to form the hypothesis and write it in mathematical form. All right, usually for convenience, you know, if you're testing the numerical value for something, usually it's convenient to give it a variable name, even though it's not explicitly given to us in the problem. Okay. And so our hypothesis in this case, so I'm going to use the symbol mu. So mu here is going to define the tensile strength or the load limit of our structural wire. Right. So our hypothesis is that the load limit of our wire is indeed 200 pounds, you know, basically what the supplier specified. Okay. So step one in this problem, fairly straightforward. It's kind of stated in the problem explicitly for us, but you know, it's good to write it down. All right, step two. Step two is to form another hypothesis, but this one's a little bit special. So we're going to form what's called an alternative hypothesis. Okay. Sometimes the alternative hypothesis is just called alternative for short. Okay. Now, the alternative hypothesis is actually very interesting. You can think of it as kind of a counterpart to our initial hypothesis, okay? But you have to be a little bit careful in terms of how you form the alternative hypothesis, right? And so you have to think about, you know, what is the situation that would be the least ideal from our situation, okay? Because the alternative is that, you know, so if the alternative hypothesis is true, okay? If the alternative hypothesis is true, then what we're going to do is that we're going to reject our initial hypothesis. If you want to kind of take this a step further, you know, the alternative hypothesis, you can think of it as, you know, if this is true, if the alternative is true, then it's actually going to change our decision making, or in terms of, you know, what we actually do with this part or with this physical situation. All right, because if you look at our original hypothesis, it's a statement of equality, right? And so there's actually three different alternative hypotheses that we can make here, right? And so one alternative hypothesis that we can make is that, you know, we can say that our load limit is actually greater than 200 pounds, right? Technically, that is different, right? And so, you know, when we're hypothesizing that our load limit is exactly 200 pounds, then an alternative hypothesis is that the load limit is actually greater than that. Okay. Another alternative hypothesis is that, you know, maybe we say that our load limit is actually less than 200 pounds. Because that also is, you know, in defiance of the original hypothesis as well, right? Because if it's less than that, that's the same thing as it's not equal to. Right? A third option is we can just simply say that our load limit is just not equal to 200 pounds. So it might be greater than it might be less than it, but you know, it's not going to be equal to 200 pounds. Okay. So all three of these, so call this option A, option B, option C. Okay. Technically, we can choose any of these as our alternative hypothesis. right? Because they all contradict the original hypothesis, just they contradict them in different ways. Okay. Okay. But in this part right here, we actually have to choose one. So we can't just say that these are all of our current alternative hypotheses. We actually have to choose one because it is going to affect how we move forward with the rest of our calculations. Okay. And so how you choose one, so sometimes the problem will just tell you. Sometimes the problem will tell you, choose the left side alternative hypothesis. But if you want to kind of think about it in terms of your original problem, right? You have to think about the alternative hypothesis that is actually going to change your decision making, right? And so, if this load limit is actually not 200 pounds, what's the situation that's actually going to lead us to change that component or change our vendor? Okay. And so if we look at option A, right? So option A, that's the first alternative hypothesis where the load limit is greater than 200 pounds. That's technically that is an alternative, and that is something that goes against our original. But this is actually something that we're not too mad at, right? Okay. Because if you think back to the original problem, right? The product that we're manufacturing relies on the fact that this wire can hold at least 200 pounds, right? If it turns out that the wire is actually better quality than we thought, right? So if in fact it holds more than 200 pounds, then we don't have to change what we do. So, we can still manufacture our product. It's just going to be even more reliable than we thought, which is good, right? And so, if you're more reliable, that's usually a good thing. And so that means that if this alternative was true, we're not actually going to change anything about our decision making. So we're not going to choose this as our alternative. Okay. Right. Now let's look at the second alternative. So the second alternative here is that the load limit is actually less than 200 pounds. So the wire, in this case, the wire is worse quality than we thought. Okay. Okay. So that is bad. So that is something that's going to change our design. That's going to change our product. Because if one of our materials here is not satisfying up to its load limit, then it's going to cause our product to fail. It's going to cause the product to break, or worse, put people in danger. Okay. So this is the alternative hypothesis that's actually going to get us to change how we actually do stuff. Okay. And so if this is true, then we actually change, our engineering process. We make a different decision. Okay. So when you're choosing your alternative hypothesis, you want to pick the one that's actually going to change or make a difference in how you're choosing your engineering decision. Okay, because this is the situation where if this is true, so if our load limit is actually less than 200 pounds, then that's going to actually cause us to reject our original hypothesis and do something different. Okay, so for this particular problem, the proper or the correct alternative hypothesis is actually going to be the middle one here, where the load limit is less than 200 pounds. Okay. All right. Any questions on the alternative hypothesis? Yes.
What about C would be the reason why it's not?
Yeah. So for C is interesting. So C is what we call kind of a double-sided alternative. And so, we don't choose C for the same reason that we don't choose A as well. And so, for C, our design here doesn't really rely on the fact that the load limit is exactly 200. It has to be at least 200. So in that case, C would also not be appropriate for. Actually, let me write that down. Yeah, so when you're choosing an alternative, I think this is probably the most difficult part of this section is that it really depends on the context of the problem. In terms of, whether you choose a left-sided alternative, a right-sided alternative, or double-sided, right? So on Thursday, we'll get more into this, but I did want to end a bit early just because I do have your midterms to get back to you. So when we come back on Thursday, we'll continue with this example, we'll finish it up, and we'll give a bit more context on how to test these hypotheses, okay? All right, but besides that, thank you guys for coming today. Come pick up your exams here. And I will see you guys on Thursday.
Friday, right?
Yes.
At 1 o'clock.
So I need to arrange another time with other people, but if you say 1 o'clock, I'll go ahead and reserve that for you, and then I'll have the others take it.
Well, I can take it at any time. Have Friday I have lab from 8:30 to 11:45.
Okay.
After that I'm finished.
Okay. Yeah, let me talk with the other formula people. and
Okay.
See what time, because I have 3 people taking.
I know, you said Bill, right?
Yeah, Bill,
Brighton?
Brighton, and
Yeah, they're in the same class that I'm in, so once
Okay.
they're finished, I think I have the same.
Okay, yeah, the range, if you guys can kind of talk in a range.
Okay.
Yeah, I'll be here all afternoon on Friday.
Okay, that works, all right. And then everything we need for the finals already posted, right? Like
Exactly.
study guide.
Yeah, exactly. Yeah, post that out.
Thank you.
For the hypothesis, will it always be between these 3 options?
Exactly.
Then you have to pick one?
Exactly.
Okay.
Yeah.
I think.